Hi everyone. Thanks for voting for my talk and attending, even though it's almost the last slot in the last day. I'm going to talk about attacking the FireEye malware protection system. Before I actually start with the interesting technical content, I have to make some introduction words. So first of all, really short introduction about me. I'm a security researcher at ERNW, which is a small security consultancy in Germany, in Heidelberg. And my main interests are virtualization and application security. And in the recent years, we reported or discovered some vulnerabilities in quite mainstream software. And we reported this in like the normal coordinated disclosure approach. We had something in Microsoft Hyper-V, open source Xen project, and also something in IBM software, which IBM doesn't have like the best reputation for like vulnerability response process, but every time it was a really smooth process. So we didn't have any problems at all, and everything was like you normally hope for when you disclose a vulnerability. In the case of this research, unfortunately, it was quite a bit different. So we have like a legal disclaimer at the beginning before I start with the actual content. So we got an injunction by the Landgericht Hamburg, which is like a German court, on behalf of FireEye Incorporated. And due to this, we can't talk about some of the details that are required to understand the nature of the vulnerabilities. We fully adhere to this injunction, so I won't talk about anything that's like forbidden in the injunction. And everything that we show or that I show in this presentation was agreed upon between FireEye and ERNW. I won't be able to discuss any details about the removed content or the ongoing legal procedures. So even if you come to me after the talk, I won't go into any details about the restricted or the censored part, so please accept that, otherwise I would get into problems. And I don't want to talk too much about like the whole legal aspect. Instead, we'll just let the bug speak, because I think even if you ignore the whole drama around the disclosure process, it's kind of an interesting from a technical perspective just to look at the security bugs. So the agenda for the talk is quite simple. We start with actually with describing a vulnerability that allows us to actually get access to the operating system of the appliance. Then normally we would go on and talk about the architecture. This part isn't included today, so this is the stuff we are not allowed to talk about. But instead we talk about two components, VXE, which is the virtual execution engine, and MIP, which is the malware input processor. And we discovered quite some interesting bugs in both of these components, so this will be the main part of the talk, and in my opinion, the most interesting one. So, just a short introduction to the FireEye MPS. So MPS stands for Malware Protection System. And it's hard to get like an exact definition what they mean with this, but at its core, it's like the core software stack that's running on every main FireEye appliance. And these appliances differ how they like collect malware samples to analyze from the network. So some of them work by just watching the network stream. Some of them are used as an email gateway, so they will analyze all email attachments. They have an appliance that uses like scans Windows file server to find new samples to analyze. And there's even a manual analysis appliance where you can like manually upload samples to analyze. And the box I have sitting right here is actually running the web MPS, so it's normally used as like a web proxy. And this is the system this research was performed on, so the web MPS operating system. But it's important that these bugs I will describe exist in all of these variants, because like the core software is the same, only like how they collect the samples is different. We won't present any, or I won't present any 0 days in this presentation. Everything I'll talk about is responsibly disclosed and is patched in the interim. So we have like a link to the notice. If you use one of these devices, you should probably already have patched, at least I hope so. Otherwise, you should do this really fast. So how do you like establish access? The initial situation when you have such a device is that you have like So in this case, this is not like a real world attack, this is like how you perform research on one of these devices. And the initial situation is that you have administrative access to the device, so you're basically the admin. This means you have access to a web interface, which is like the main user interface used during normal operation, which gives you like reporting and analysis stuff. And you have a command line interface, which is reachable via SSH, but this doesn't give you like a real shell. Instead, you have like an iOS, so like a Cisco iOS shell, which only has like a wide list of enabled commands, which is quite restricted. So if you really want to find out interesting vulnerabilities, the one in the analysis process, then you have to get an operating system to the underlying operating system of the appliance so you can really understand how the analysis works. So if you look at the web interface, I can't show you the web interface on this device, and I can't show you a screenshot. I'm legally prohibited from that because the design of the user interface is intellectual property of FireEye. So I have to like do it text only, basically. So the web interface allows you to configure, use TLS certificates as well as certificate authorities. So you can use to like configure basically the SSL service. And if you upload a certificate using this web interface, it's basically just passed into OpenSSL, like the command line tool of OpenSSL, to perform some kind of validation. So it looks how, if this is this a valid SSL certificate, is it still valid or is it too old and stuff like this. And if you upload a whole certificate authority bundle, they have this two-step process. First, they just validate the whole certificate bundle by passing it into OpenSSL. And then they split the bundle into multiple chunks. So they just search for end certificate because this will be at the end of every certificate included in the bundle. And then they pipe the single chunks to OpenSSL, pass the output to, again, perform these kind of validation, but now for every certificate in the bundle. Now, if you ever have worked with OpenSSL or like the command line tool, you might know it's pretty like relaxed about what kind of input it accepts. The only important thing is like the stuff between the begin certificate and the end certificate, but at the beginning you can like just put into like arbitrary junk. And if you look back at the pseudocode, they basically have an echo and pipe it into like a pipe. So if you just start your junk with like double quotes, you break out of the quotes, and then you have a completely standard trivial command injection. So this is nothing too interesting, but it gives you a shell. So I have a demo for that. As I said before, I can't show you the web interface, so you can actually exploit this using your browser because you just have to upload a fake certificate bundle. But because I can't show you the web interface, I just wrote some crappy Python script which just basically performs the 2 HTTP requests you need. And yeah, you can see I log in with a hard-coded password. So I have like a valid, this is post-authentication, so I have valid credentials for the device, and I get a shell. And every time I get a shell during this presentation, this is like the difficult part for me, because I only have like a really restricted number of comments I'm allowed to enter into the shell, because otherwise I would leak intellectual property. So I will just enter who am I, and you can see I'm the web UI user, so I have low privileges, but I have a working shell on that. So that was the first demo. Now, that was not too hard. It was more like a small exercise at the beginning, but it's like the required first step. So this is something a lot of people don't understand if they're talking about like vulnerabilities in these kind of devices. These vulnerabilities in the web interfaces are completely uninteresting for every real world like environment. Because in this case, it's even post-authentication, but even it would be pre-authentication, it's still uninteresting, because normal external attacker would never have like internet or connectivity to this web interface port. This is hidden somewhere like in the internal network, so it will never be able to just connect to the web interface. So this is nothing too interesting for real-world attacks, but it gives us the needed operating system access we need to like find the more interesting bugs. And then the next step, so first of all, if you want to perform like in-depth research on this device, you want persistent access, so you don't want to exploit this bug over and over again, and you want to be privileged, so you need like a root account. The privilege escalation is in this case quite trivial, because they actually, so if you boot up the device and you configure it initially, you give an administration password, and they use this administration password also as the password for the local root user. So you would normally never be able to like log in as root to the operating system, but if you have a shell, you can just use as you, use your configured password, and you have root. Now, for the persistence, you basically just, so the root file system is mounted read-only, so you just remount it as a writable, and then if you replace one of the command line interface comments, so the comments that can be used from the restricted iOS-like shell and replace it with a symlink to bash or something, then you can like break out of the restricted shell into a real operating system shell which will run with root. And like the easiest way, for example, is to replacing the telnet binary that's callable from the restricted shell with a symlink to bash, and then you just log into the box normally, enter telnet, and you have a root shell on it. So this is like the first steps. Now what comes next? And this is like the bit of a general slide. If you have like, from my perspective, what's the goal on research on these kind of devices? You want to understand the attack surface. So what possibilities offer they to an attacker to compromise them? And you want to understand the advantages and limitations. So what can they really, and what are they quite good? So what are attacks they easily detect? And what are the like kind of limitations? And for this, and somehow an understanding of the system architecture is required. So you would normally need to know, yeah, these are the components involved and these are the ways they talk to each other. So normally we would have something like an architecture slide. In this case, we don't have it. So I can't really say much about like how this thing works in like in a global context. But as you can imagine, there might be some static analysis involved and dynamic analysis. So if they get a malicious sample somewhere out of the net or out of an email attachment, they perform at least these two types of analysis. It's not too surprising probably, but we have some kind of static stuff and also like the dynamic analysis. And the two most important components for these are the VXE, which is the virtual execution engine, and it's like one of the main components involved in this whole dynamic analysis process. And one of them is the malware input process, or MIP, which orchestrates the whole static analysis process. And now, in comparison to the first boring bug, we have a completely different attack scenario. So if we find a bug in one of these two components, then the only requirement for a successful attack is that the file of our choice is analyzed by the appliance. And this is, for all real-world environment, this is trivial to trigger. Like, you can just send a mail with an attachment to an arbitrary employee if it's like used as a mail gateway, and the employee doesn't even have to open the mail. It's not like spear phishing. It's even better because you just send some kind of word attachment or something that exploits the bug and analysis process to an arbitrary email address in the company, and this already will trigger like the analysis process by the appliance. Just transferring the file is enough. So, about the virtual execution engine, I can't tell you too much. It's a virtualized environment to run malware on. And it has several interfaces to the physical host system. But I can't tell you about the interfaces to the physical host system, at least about one. And this is like the most interesting one. It's a shared library called libnet control_switch. And so you have to imagine if you analyze a malicious botnet or something, so you have an executable that you are running inside this dynamic analysis environment, then it might generate network packets, so it wants to talk back to its command and control server or something like that. And of course, you don't want to simply pass these packets onto the normal network. It would probably not be a good idea. Instead, these packets are directly passed to this library. So they'll just take the raw bytes and pass it into the correct function inside this shared library. And these libraries then responsible for generating sane-looking responses to keep the malware running. And when the packets are passed, they're then passed to either the DNS handler or the IP handler. So DNS handler, as the name suggests, just handles DNS requests. The IP handler handles everything else. The DNS handler is also very simple. So it just logs the requested host name and then returns like a faked response. So it just fakes DNS responses to point them to like arbitrary IP addresses. But the IP handler is much more interesting. And one interesting property of this handler is that they have like a mechanism for protocol detection, because you have to imagine they can't simply perform protocol detection based on the destination port. That wouldn't work in most cases. So instead, they have to like somehow detect the protocol by looking at the payload. Whenever you get like a TCP packet or an IP packet to a new host, the information about this host is stored in an address structure. So this is like a global structure for each IP address you connect to, which contains all the data corresponding to this host, so all the state information and stuff. We will discuss this in more depth later during the exploitation, but basically it has like fields for IP addresses, the DNS entry, and some internal states. And it stores a table of 10 port structures, which are like the same, but for a TCP port, so for a single TCP port. And they are all stored in some kind of hash map combined with a linked list. So every structure has a pointer to the next and the previous address structure with the same hash. So if you ever exploited something, you can probably already get where this is going later on. Now, if you send data to a new TCP port, then they initialize a state machine. And the state machine works by, or the first step of the state machine works by just taking the first 12 bytes of the TCP payload and then converting them to uppercase. And this is kind of a crude approach, but they basically just check then for hard-coded protocol indicators. So if they see a GET, they know it's HTTP. If they see a NIC, they know it's IRC and stuff like that. So yeah, well, it's a way you can do that probably. And then when they have detected the protocol based on this technique, then they try to respond like in a semi-realistic way. So if you have like an HTTP request, they will return with an HTTP response to keep the malware running as long as possible. And they try to simulate normal protocol communication. Now, if you look at the code quality of this module, it's kind of not state of the art, I would say. So the first bug I found is a /nic overflow. And the bug is triggerable, so what happens if you send /nic followed by a name, then you get a welcome message back from the simulated IRC server, like, hello Nick, welcome back to blah 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 server. Of course, this message includes your nickname, and the message is generated using the sprintf function. And as destination for this sprintf, so sprintf doesn't have a length restriction if you ever have written C code. They use as a destination, they use a stack-sized buffer, stack buffer with a size of 1024 bytes as the destination of the sprintf. That's like the most 90s style stack buffer overflow you can ever imagine in this kind of code. Now, how do you like trigger this behavior or this bug? Basically, you write your own malware. Like you can choose something, arbitrary programming language that will turn out a binary able to run on Windows. So this is like pseudocode to just connect to inthebox.org to an arbitrary port. It doesn't have anything to do with like IRC. It doesn't have to exist. So it's just, this will never like really work on the real network. It's just triggers like the emulation. And then just /nic followed by a lot of 8s. And then you trigger the analysis, for example, by mailing this, this file or this executable to some kind of employee using this device. And then several things could happen. So my first impression was, yeah, probably you get something like stack smashing detected, because like every compiler in the last, I don't know, 8 years or something has like stack smashing protection features. But instead you get like the traditional 4.1.1.1 direct IP control. That's kind of impressive. Now, if you then want to actually exploit that, so we want to get like control over the instruction pointer, you have like fixed stack buffer, so that's quite easy. You don't have any stack cookies, also good. And the virtual execution engine binary itself doesn't support position independence, so it's always mapped at the same address. So you don't even have like full RSLR. So at first I thought, yeah, that's like trivial to exploit. Unfortunately, if you then, it's like, this is the problem with these kind of vulnerabilities, that nowadays on a 64-bit system, they are actually not that trivial to exploit. In this case, the virtual execution binary, so it's of course mapped somewhere in quite the beginning of the address space, while the shared library we are actually exploiting sits somewhere down in the high range of the address space. So if we want to like point into a return address inside the virtual execution engine, we need the ability to write 0 bytes, because all virtual execution engine addresses include much more 0 bytes than the one in libnet control switch. So this is quite difficult because our nick, like the nickname, only is allowed to contain ASCII characters. So we can't not put 0 bytes in there. And the main problem is normally you would try to do a partial override, so you just override like the last byte with a 0 byte or something. But that's also not possible because we don't control the last bytes of this welcome message that's generated. Instead, like the last 5 bytes or something are controlled, are static values, so we can't play around with them. So in the end, this is kind of hard to exploit. Probably if you spend a lot of time on it, you might have a clever idea how to exploit this. But I decided just to look for a couple of other bugs, because like this was the first thing I found, and then you probably have good chances to find other more easy to exploit bugs. I already mentioned the port structure. So this is the one that's created for every TCP port that you connect to. So you have the address structure for every host, and every address structure has 10 port structures. And this port structure contains a number of inline buffers with the same nice size, so 1024 bytes, named nick info, join info, and so on and so on. And they are filled after using the get value function when a certain keyword is detected. So the nick info buffer will be filled after they see a nick, then they call get value and use that to fill these bytes. And the same for join, user, and whatever. So you can just enter like this keyword and put arbitrary data after that, and then these data will be copied inside these buffers. Again, get value copies till it finds a 0 byte or a line break, so they don't have any kind of length restriction again. So you have like quite a lot of overflow possibilities. And now in the next slide, I have a couple of diagrams, and just for that, another disclaimer, so all of these diagrams are just here for illustrative purposes, and they do not describe any architectural design or specific of FireEye products. So just keep that in mind. These are heavily simplified illustrative diagrams. So this is like how this port structure might look in memory. And you can see they have these inline buffers just after each other. Now, whenever you write basically 1024 bytes after join / nick or user, for example, then you just override into like the next buffer. Your override size is limited by the MTU of the emulated network card. So you can't simply send a single packet which contains like 50k bytes. Instead, you have something like 1,400 or something. And this makes only the join info overflow actually interesting, because if you overflow nick info, you will just override into user info and won't override or corrupt anything interesting. Just join info, which is at the end of these inline buffers, seems to be interesting. if you look at, like, unfortunately, this data at the end of the PodStructure isn't interesting in itself. So it's not something that you just corrupt like the last bytes of the PodStructure and you get anything interesting going on. But as I mentioned before, these PodStructures are stored inside an address structure. So it's just one really large, you can imagine, you have 10 of these which include all these inline buffers, so it's a quite large structure in memory. And they are stored in a variable or in a field called port table. You have 10 of these port structures, and afterwards you have this previous and the next pointer of these linked list. So what you can do is, if you trigger an override in the last port structure, then you can corrupt the previous and the next pointer of this linked list code. Triggering this is still pretty simple, actually. You just connect to 9 different TCP ports on the same host. This will fill up these 9 port structures, and then you connect to a 10th port and actually trigger the overflow. And if you do that, you just get a crash somewhere in this linked list handling code. Now, first, you still have the same problem you had with the first bug, the stack overflow. In this case, again, we can't put 0 bytes because get value quits when it sees a 0 byte. We are in a 64-bit environment, and of course the heap is randomized. So it's not like the heap allocations are always at the same constant address. But this time the difference is we can perform a partial override, because like at the welcome message generated by the FTP server or by the IRC server, always had like this last fixed bytes, but in this case, join info is completely under control, so we can do a partial override. And now, the interesting thing about this is that this address structure, as I said, is really incredibly large because it has all these inline buffers. And the malloc implementation used by the system has the behavior that if you allocate a certain amount of bytes, so larger than this boundary of hex 20,000 bytes, then they directly go to mmap. So they don't use like the normal malloc chunk allocation stuff. Instead, they just use mmap to get pages from the kernel. And this will trigger the behavior that this malloc chunk that is returned using mmap will always be at the page boundary. And then you have like the normal malloc metadata in front, which means the least significant byte of the structure address is always hex 10. So while all other bytes are heavily randomized, so you're not able to simply like brute force this or something, you always know like the last byte or the least significant byte of this address is in hex 10. Now this is how normally these two address structures would look like in memory. So they are like connected using this next pointer and previous pointers, linked list, I guess. And the least significant byte of both of these pointers always equals hex 60, because in this case it's hex 60, not hex 10, because they don't point at the beginning of the address structure, but instead they point at the beginning of the linked list. So the actual traversion would then calculate the offset or use the offset to exec the struct. Now, what happens if we overflow this join info buffer? So we use this override to corrupt the previous and the next pointer. And then we only override the last byte of the next pointer with the final 0 byte generated by getValue. So we have like 1 0 byte we can use, and we use this to override the least significant byte of the next pointer variable. And this leads to the case that now the next pointer doesn't point somewhere here, but instead points directly inside the port table. And luckily, it's by random chance, it points again into this join info buffer of the second structure. And this is again something we completely control. So now we have like, we can create another faked pref and next pointer inside this join info buffer. And still doesn't look too nice to us, but the good thing is this join info is initialized with zeros. So this means, like in this case, we only had the ability to write one single 0 byte like at the least significant bytes. But now, because this address is like initialized with zeros, we can now create a pointer with an arbitrary number of leading zeros. And we can use this to point into the memory of the virtual execution engine binary itself, which isn't randomized. So this gives us all we need to perform a stable exploitation. So the idea how you then do this is that you have like a pointer to a fake address structure. You point this a couple of thousand bytes before something interesting to override, because then later on, if you actually send data to this fake address structures, it will just copy the bytes into this destination buffer and then override the target. Again, this is possible because we don't have position independence enabled for the VXE binary. So you simply need a connection to a host that matches the IP address inside the stored, inside this faked address structure, and then you get a write primitive. Now, the thing that cost me embarrassing much time, because it's quite easy at the end, is that you have certain requirements for this location of the fake address structure, because the fake address structure has to look at least somehow legit, so that later on the override works. So for example, the first offset, like the offset 0, contains the hash of the IP address you want to talk to, and this has to be unequal to 0, otherwise you won't be able to connect or to use this address structure. And the most problematic one is basically that you have a certain offset, and then it's a 32-bit integer value that's only allowed to be 2 or 3, which is kind of hard to find inside the data segment of this binary. I tried at first to do this manually, but if you just take in mind that you have if we find such an offset, we can corrupt 10,000 of bytes after this point. So we are quite flexible where we point this fake address structure to. And if you just write 5 lines of Python to check for these requirements, it will spit out 12 usable locations in the virtual execution engine data segment, which we can use. And then it's quite trivial, because if you have the location, you get multiple function tables that you can corrupt. I can't tell you which function tables there are, because again, that's not in the part I'm allowed to tell you about, but it's a function table that gets called relatively often during the normal operation. So we just corrupt them, so write our own pointer value to it, and then we get instruction pointer control. And then it's really trivial to find a stack pivot that just pushes the RSP into our controlled buffer. So we have a wrap chain, and then with 2 gadgets or something, you can just jump into system and get a shell out of it. So it's the last step of the exploits are not too interesting. Now what's interesting is, this is again another example. If you don't provide the vendor with a full code execution sample, they won't believe you it's code execution. So we sent them, when we reported the vulnerability, we sent them a proof of concept that triggers a write violation somewhere in the linked list implementation, and they still considered this a moderate vulnerability because it can only cause a limited denial of service. I mean, just the virtual execution engine crashes, but nothing bad can happen. Of course, that's not really the case. So I have a demo for that. Let me check. So I have a web server, and I need to trigger the analysis. And I do this by downloading this executable, which contains the exploit code from another system. And the FireEye watches this network interface, basically sees the download, and will then start to analyze the sample. So this is how I will trigger this for this demo. I just have to make care. So each appliance, they only look at this exploit one time, because they will start it, will be exploited, and then will say, yeah, that's a harmless sample. And they store the MD5 sum of the sample. I will never look at it again. So I have to recompile my sample every time I want to demonstrate this. So I just have to take care. I have a new sample inside there. And I will start a Metasploit handler, which is just waiting for the reverse connection of my shell. And what you should see soon is we see a download of the tiers.exe, which is like the actual exploit code. And if the vulnerability is exploited, then the FireEye appliance will download c.py, which is like the metapreter reverse shell. So I just go system and grab a Python reverse shell that I then execute. So if we see like a second download here, we know the metapreter shell should be started. So let me check and start the download. Yeah, you should see the file was downloaded. So I can now see the analysis process on my shell on the appliance, but you won't see anything of that. Again, I can't show you, unfortunately. But it takes some time, but then we should see the download of the c.py file. And if that happens, our shell will be executed. So again, I do like the sample generates a lot of network traffic to like generate all the objects needed and connects to multiple ports. So this takes quite a bit until the exploit actually finishes. But it's still running, so we should see something soon, I hope. Sometimes the appliance doesn't like my samples anymore, so then I have to reboot it. So it's like it just ignores malware and doesn't analyze it anymore. But that seems to be a general stability problem of the box. Let me check. Oh, now something happening. That looks good. So I can see if it detects some kind of network anomaly, and now it started the actual analysis process. That makes the demo more exciting if it takes a while, otherwise the exploit would be quite boring. Yeah, now you see we have the c.py, and that should normally trigger. Let me check. Of course, it worked like the 5 times I did it before the talk, but doesn't work during the talk. Let me quickly check if I see the problem. Oh, sure. If you don't start a handler on the my Metasploit reverse handler was only listening on like the local host, so that probably doesn't work. So let me check. I just triggered the exploit another time. You can actually see the download was triggered twice because it will try to analyze my malware on different operating systems as well. But it probably won't trigger a third time, so I have to recompile the sample again. Copy the new sample. I triggered a new download of the tiers.exe. Yeah, now it should work. I still have 20 minutes left, so I calculated a bit of time for the demo. also quite a pain in the ass to actually take this thing with you on the plane, because it's quite heavy, and border control, at least in England, was quite interested in why I would take something like this on the plane. Now you can see we got the download again, and now I got my Metapreter shell working, so we got the stage. And I hope the fucking stager doesn't crash this time. Kidding me? Okay. I'll do it one more time in the background, and then I'll just continue with my slides while I check if it's okay. Okay, so as you all saw, it's 100% stable. No, it's good because I have my next bug is more stable exploit. So because we have a technique that bypasses RSLR, we have several requirements for the fake address object, but the target is large enough to find this stuff. But the big problem, if you would want to exploit this in the real world, so you are completely outside of the target network, you never talk to anyone on the target network, and then you don't really know what version of the virtual execution engine they use, and you need this for the stack pivots or for the gadgets. So you can kind of build an info leak out of this bug, but it's really difficult. So you won't get 100% reliable code execution out of this issue. So it's a nice bug, but you probably won't find real world exploits targeting this in the wild. Now, we still have a component left. So this is the stuff where you would look at if you want to really exploit this in the wild. And this is MIP. MIP is responsible for the static analysis. And the responsible, it's called or stands for the malware input processor. And one interesting design decision about this malware input processor is that it's actually running on the host system. So it's not running in a virtual machine, instead it's running on the normal operating system. Which of course means that if you have a vulnerability that exploits the malware input processor, you are not anymore in some kind of VM, instead you're directly on the operating system and have compromised the appliance. MIP supports a significant number of different file types, but I can't tell you about those. But it also supports zip. So that's you would have guessed that, I probably think. And how they do this, so they support zip because at the end, if you send your binary or your malware inside a zip archive before it's passed to dynamic analysis, the malware input processor has to extract it, because of course the zip file won't do anything interesting in the dynamic in the virtual machine. Instead, you want to run the actual executable. To extract zip archives, they decided to use P7zip, and this is an unofficial fork of the normal Win32 7zip, which supports POSIX systems. And they have a Python script called extract_r.py, which performs the following call. So it just calls into 7zip and it extracts the content in a local temp directory. Now, I thought might be an interesting fuzzing target. I mean, P7zip is not state-of-the-art production-hardened software or something. It's just some kind of open source project. Maybe let's first look for open bug reports. And interestingly, a guy named Alexander Cherepanov reported a vulnerability that allows you to perform a directory traversal by embedding a 7zip file inside, by embedding a symbolic link inside a zip or 7zip file. This allows you then, so when 7zip extracts the archive, it will follow the symlink, which means you can like extract data into arbitrary directories on the file system. So you have a directory traversal and like you can create arbitrary files. So this bug wasn't fixed in the appliance, or they didn't know about it. And this already allows us, if we create a zip file or 7-zip file with a sibling to a writable directory, and then trigger analysis again, the MIP will extract the archive, follow the sibling, and allows us arbitrary file creation in any directory that's writable to the MIP user. You can also do like file overrides, because interestingly, they passed a -y flag to 7-zip, which just means normally it would print out some kind of warning, I don't want to overwrite this file, and you have to manually agree on that, but due to this flag, you can just overwrite any writable file. They did it right by restricting most of the importance directories, so they're normally not writable for the MIP user. But there's one really interesting one, which I can't tell you. We name it censored in this context. But this directory is writable by the MIP user, and it includes the static analysis scripts for all the different file types. So when they will see like an RTF file or a PDF file or something like that, they will call the Python script with the logical name. So rtf.py is called whenever analysis of an RTF file is performed. And interestingly, the files itself are not writable, but the directory is. And Linux directory permissions work like if the directory is writable, you can just override every file in it, even if you don't own it. So in this case, we can just override rtf.py with our own backdoored version. And now, how do you turn this directory traversal to a code execution? You just create a malicious zip archive containing the symlink to the censored directory and a backdoored rtf.py file, pack it into a zip archive, and then you send that to some kind of address at the target company. So for example, maybe sales, or even something that someone who's probably on holiday and doesn't read his mails or something like that. And this will already lead to the analysis process, extracting the zip archive and overwriting our rtf.py with the backdoored version. And now, whenever we send another mail to an arbitrary email address at the company, and we just attach an arbitrary RTF, so it doesn't have to be malicious. It just has to have the right file type. This will then trigger the static analysis module, which in turn will execute the rtf.py, and then we just wait for our shell to pop. And this is a cool bug, because this is like 100% reliable code execution against every device vulnerable. And every device vulnerable means version 1, like the first stuff they ever released, to everything not patched after we reported this. And imagine you just push an email with this zip archive out to some kind of popular mailing list used by security professionals or something like that, just because the guys are grabbing the emails from this mailing list automatically, you will probably get dozens or hundreds of shell out of this vulnerability. So that's it's nice from in the wild exploitation. But still we have like one small problem. The code is only running as low privileged user. So we are still running as the MIP user, which has kind of not too interesting privileges. To fully compromise it, we would need a privilege escalation vulnerability. Now luckily, there's something called cms_agent.rb, which is a Ruby script running on the system, and it's running with root privileges. It seems to be, so CMS stands for Central Management System, so it seems to be for like connecting multiple appliances and managing them like a single one or something. But for our case, the most interesting part about it, that it's root, it's running as root, and it has a TCP port open, so that's only reachable over the local host interface. And it implements a dRuby server. And now if you never heard of dRuby, that's an RPC mechanism for Ruby. So you can just call arbitrary Ruby methods and exchange objects over the network. So it's like a bit like Java RPC stuff, just for Ruby. And they have like a whitelist, so you can't call arbitrary methods, but you can call the mdreg_exit method, and that simply takes a string argument and passes this directly to a command invocation on the command line without any kind of checks. So again, this is like a really trivial, simple command injection. And if you combine these bugs, you get like 100% reliable root with just a zip archive, which is kind of nice. Now let me check if the exploit worked in the meantime. I don't know why that's happened, to be honest. So as you can see, it's actually, so that the appliance is connecting to the Metapreter reverse handler, but it's not triggering the final execution. Let me check if I did something wrong. Because unfortunately my second exploit also uses Metapreter as a reverse payload, so if my Metapreter listener isn't working, it will still, oh, yeah, I'm stupid. Okay, so I will do first, we will do the zip archive because I'm sure that works and it's fast, and after that I do the last try of the memory corruption bug. So again, it's quite similar to the first exploit. So we still have like my HTTP server running, and I just generate a new version of the zip archive. And if I then trigger a download of the zip archive, so you can see I downloaded the zip file, and this already, so this backdoored the rtf.py file, but nothing else will happen as long as no RTF file is analyzed after that. So this is like a silent backdoor sitting on this appliance. And what will happen if I then actually download an RTF file? Is, as you can see, I got a Metapreter and now the session opened. I think I can do get UID. Yeah, you can see I'm running as the MIP user, so it's kind of lowly privileged. Again, I just have to be a bit careful which can't do clear. So I'm like still the low privileged user. If I now have my local root exploit, which just is this Ruby script connecting to the druby server, and I do something like ID, you will see I'm root. So this is like the last step you need for like a full root compromise of the device. Okay, and now because this one worked, we also will get the other one working. So I quit the Metapreter again, start the exploit again. And rebuild my Desist.exe. So again, you see the ts.exe is loaded. This will start the analysis process, and I just finish with my last slide, and then hopefully at the end we'll finally the Metapreter for this exploit. So if you just look at the zip demo already, you know if you haven't done it, you should get these appliances patched right now. So it's like really, if you only take away one thing from the talk, then patch this. And now we have some kind of conclusions. So how could you prevent something like this from happening? In the end, if you have something like dynamic analysis running on these devices, you should use some kind of hardening measurements. So the memory corruption exploits would be really hard to exploit if just the normal compiler hardening mechanism would be used. So if you have stack protection or position independent executable. If the static analysis process would be instead just executed in a virtual machine, then like something like compromising the malware input processor wouldn't happen because you would be like directly on the host system. You still need a hypervisor breakout. And of course, something like hardening all local privileged processes would have helped against the local root vulnerability. And this is something like a general recommendation. If you have like parsing code that parses network packets or I don't know, file formats, then implementing in it a memory safe language would be probably a great idea. But still, if you have all these mitigations and all these mitigations work, then you still have to accept that if you use these new capabilities that you are gaining by using virtual machines to like detect APT attacks and stuff, you also have a much larger attack surface or specific attack exposures that the vendor needs to keep in mind and that you as a user of this product probably also has to keep in mind. It's just the simple, if you have just like some kind of packet filter that just works on IP and does some kind of filtering, you probably won't find that many remotely exploitable bugs in it. But if you have something that works with a virtual machine and performs heavy analysis of malicious samples, then it's probably a significant attack surface, and you have to keep that in mind if you're using these kind of devices. And before I'm completely finished, I still have a timeline left. So this is like, again, not the technically interesting part, but it's a bit about the disclosure process. So our initial attempt to contact or to report these vulnerabilities to FireEye was the 7th of April, where I sent a PGP encrypted mail to security@fireeye.com and didn't get a reply. I tried to like send an unencrypted mail asking if they got the last mail, still no reply. And then, as you do, after like 20 days of waiting, I just asked on Twitter if anyone could like give me contact information of some guy working at FireEye, and that helped. I got the information, and then we got an immediate response. After that, we had like a lot of conference calls going over the whole disclosure process and which stuff should be published and whatnot. And we even had a face-to-face meeting with the guys from FireEye in Las Vegas, where we again like discussed the details in our report and how much we could like talk about. And our impression after that face-to-face meeting was that like some kind of agreement was reached. So we were kind of positive after that meeting and everybody should work out. Unfortunately, the day after, our German office got sent a cease and desist letter from FireEye, requiring us to like sign something, we won't talk about the stuff, and we should sign it by Monday, which was kind of, so this is a Friday, we were in the US at Black Hat, and they required us to sign something by Monday, which is kind of not good style, I would say. And at August 13th, they finally got an injunction issued by the Court of Hamburg, which basically forbid us to talk about all the stuff that was censored in these slides. So this injunction stuff is still ongoing, so I don't have any updates on this side. Now I still have a minute left, so let's check at the final exploit. Of course, it still doesn't work. Yeah, but I know what's not working probably. Yeah, I just have a last slide, so the question and answer. So if you have any questions, thanks for your attention. I'll take a look at my screen while we're doing the question and answer, so if the exploit pops up, I have the demo working. Otherwise, I can show it to you in private as well.
Thanks for the great technical talk.
Thanks.
I just checked Wikipedia, and MD5 collisions take...
I have problems understanding you.
Sorry. According to Wikipedia, MD5 collisions take a few seconds to calculate these days. You said that if the system had seen an MD5 already, it didn't rescan the same content? So
I hopefully just said hash value.
okay.
If I said something else, it doesn't contain any details about the inner workings of the appliance.
Any other questions? No?
Okay, then thanks again. Thanks for listening. Sorry the first demo didn't work. Hope you still enjoyed the talk. Thanks again.
Thank you very much. Thank you, Felix.